be able to speak in this venue to this audience, and on this occasion in particular, I'm really honored that Fulvia began and you got to hear her thoughts. I remember when I just was starting in graduate school and had no real idea of what statistics was about. Really the first few weeks, I was a graduate student at Harvard, and Harvard then had a very strong group in exploratory data analysis, graphical methods, missing data, that sort of thing. And also there was Art Dempster, who was a very Bayesian and beyond, upper and lower probabilities, and I didn't know anything, and I just really was trying to figure out, what is statistics about? What are we doing? What am I supposed to do? And didn't really know, and I went to the Harvard bookstore, and I was looking at the books the way we do, and I saw this book, which I'm sorry, that's the best we could get, but this is really a true story. It's Finnetti's Probability, Induction, and Statistics, and I was just standing there and kind of opened it up and started to read, and I couldn't put it down, and I was poor as a church mouse, and it was, $80 or something, and I bought it, and I started to read it, and I'm still reading it. I really recommend it. It's perhaps the most accessible introduction to his work and writing. My first paper, my first paper on my own was about Finetti's work, finite forms of Finetti's theorem on exchangeability. And the last talk I gave, which was last Friday, was work with Sergio Baccalato and Susan Holmes, Finetti's priors using Markov chain Monte Carlo computations. So from the beginning to the end, I have spent a career trying to understand in my own language what Finetti was talking about, and I'm not going to try to do that today. I set myself an impossible task today. The thing is that statistics has changed since Finetti worked. It's not that the ideas aren't central and valuable, but something's changed, and what I want to try to do is, at least for 1 second or for 50 minutes, to try to think about what would Finetti, what might he do if he were doing statistics today? Okay, so I want to look forward. And of course, the thing that's changed more than anything is the computer. Just enormous data sets, but our ability to actually do Bayesian analyses in real time, in particular Monte Carlo simulation, is just every place. And so I want to think about that, and what might Finetti think about that. And so first, here's a little paradox. I don't know if that'll work. So thinking about Monte Carlo data, and the paradox of the problem is this. Why do we Bayesians, and me too, why do we Bayesians, when we analyze the output of our Monte Carlo trials, use frequentist methods? I never see anybody do anything other than X bar plus or minus 2 standard deviations. I mean, people say different things, but if you look at what we actually do, what's been in every... Now, it's not only the Bayesian's problem. Statisticians don't use modern statistical methods. They use X bar plus or minus 2SD, if they do plus or minus 2SD. And so what can we think about? Now, why is that? Now, of course, the first answers are, for many cases, maybe most cases, the extra thinking, first of all, it's difficult. You've got to slow down and think about every Monte Carlo. Come on, it's costly, and then it's not worth it. The basic findings is that the data swamps the prior, and if you've got a lot of data, the prior won't matter, and so why bother to specify a prior? And that's all true and valid. And what I want to talk to you today about are some problems where it seems to be worthwhile, where it's not, the data doesn't swamp the prior, and maybe there's something more to be found by incorporating what we know. Here we go. So this is an example, and please try to follow this because this theme runs throughout, and it's a simple example to follow. When I first came to Stanford, 1974, Don Knuth, the world's greatest computer scientist, I call him, and wrote me a note saying, hey, I have a statistical problem for you, okay? And he was trying to count how many paths there are in a 10 by 10 grid, that's a 10 by 10 grid, this one here, which start at 0, 0 and wind up at 10, 10 and don't intersect, okay? So here's an example of such a path. Here's a path which is in a 100 by 100 grid, but take the 10 by 10 case. He wanted to know how many such paths are there. This is a well-posed question, and the number of paths, these saws, self-avoiding walks, the growth rate of those are fundamental constants in physics and chemistry and in biology, and it's not a frivolous question. And he had an algorithm, which, let me explain the algorithm. The idea is to grow one at random, and so let's suppose you start here at 0, 0. So half the time you go up and half the time you go to the right. Say you go up, okay? And then here I could go up or to the right. I can't go back, so maybe I go here. And now I could go up or to the right or down. Suppose I go down. Now I'm not stupid, I don't go back. You know, I have no choice, I have to go here. Now I could go here or here, suppose I go here, and now I could go here or here. So you understand what I mean. You could grow one and you make the choices at random, uniformly from the possible choices you can make. It's easy once, you might get stuck, okay? You might get stuck. Whoop. It turns out it's easy to check and not get stuck, but suppose you're not so smart and you're just running the algorithm. If you're successful and you make a path that goes from 0, 0 to here's to 4, 4, sorry, you could calculate very easily what's the chance of the path that you took. That is, I'm going to call the paths gamma, and the chance of gamma, well, it's a half times a third times 1 times a half, and so forth. You could just multiply the probabilities along the path. Yeah? Is that okay with everybody? I hope. Thank you. Now let's make a statistic, which is t of a trial is 0 if you get stuck, and 1 over the probability of the path if you're okay. So that's a perfectly computable statistic. What's its mean value? Well, its mean value, the expected value of the statistic, it's, of course, 0 if you get stuck, so it's only the sum over all possible paths, because otherwise it's 0, of the statistic times the probability that you've chosen that path. Now, the statistic is 1 over p of gamma, and the p of gammas cancel, and you're left with the number of paths. So this is an example, a classical idea of what's called sequential importance sampling. But if you haven't seen it before or don't remember it, it's sort of magical. It's an unbiased estimate of the number of paths. And Knuth ran it, 10 billion times, okay? Really did run it 10 billion times. And he got estimates. His estimate for the number of paths was 1.6 plus or minus, 0.3 times 10 to the 24th. The average path length was around 92. Now it's a 10 by 10 grid, so that means typical paths really almost cover everything. It's surprising a little bit. He found, 81% of them went through the middle vertex, and his problem was this. He said, I ran this thing 10 billion times, and, suppose I'm just calculating this statistic t, and you run it at its, 10 to the 17th, 10 to the 19th, whatever it is, but then one value, you know, this is a product of a lot of little numbers, so 1 over it can be very big. One value overwhelms everything that came before, a typical problem that we have in importance sampling. And he thought, you know, do these numbers mean anything? He understood that that was a problem. And it's a problem for us today when we use any version of importance sampling, and that's a very common method. Okay, so there's the question, do these numbers mean anything? There's huge variability, as usual, for importance sampling. It seemed as if 1 million samples were determined by 1 or 2 numbers. Nowadays, people do a funny thing. They calculate an estimate of the sample, the effective sample size. Well, that's the standard deviation. If the mean doesn't mean anything, the standard deviation means much, much less. Okay, and then there's a question, is there more information that we have about the problem or that's in the data that we could use to help with this problem? And just to explain to you that there's something to understand here, about 10 years after Knuth, he published this analysis, his work in Science, and about 10 years later, some physicists got annoyed and said, 10 by 10, we'll blast it out. And they just blasted it out. And these are the numbers. Knuth's estimate of the number of paths was 1.6 times 10 to the 24th. They know the exact number. That's not so helpful, but this is more helpful. It's, you know, 1.5687 times 10 to the 24th. It seems to work pretty well. And his other numbers were spot on, too. So there's something to understand, okay? It's not just crazy. It seems to work, and do we have anything to say about it? Okay, so if you don't mind, let me try to think out loud, and I'm very eager to have feedback about this. What do we know? I mean, because do we really know, you know, anything? So the first step is to give it a name. So let's let theta n be the number of self-avoiding walks from 0, 0 to nn. And that can shock some people because it's a perfectly determined number. You know, it's just some number that exists in nature. And if you haven't thought about that before, you know, think about the 37th digit of pi. That is, for most of us, you don't know what the 37th digit of pi is. For me, you know, it's equally likely to be anything from 0 to 9, and I'm perfectly happy to bet for small amounts on it. Now, my math colleagues are always trying to figure out, what do statisticians do? And so I said, oh, well, think about the 37th digit of pi. And one of them said, the first guy who computed 796 digit of pi, the first mistake he made was on the 37th digit. I said, oh. And the second guy said, the 37th digit of pi past the decimal place is 0. So, of course, different people have different knowledge bases and, you know, different priors, of course. And now you know what the well, you have a reasonable mass at 0 for what the 37th digit of pi is. But, of course, as Bayesians, we're allowed to put priors on things that we don't know. And the number of paths in a 10 by 10 grid is really something that we don't know. So we know something about it. For example, this walk, each time that you take a step, you can take at most 3 directions. So the total number of paths can be at most 3 to the n squared. It can't be any more than that. Now, if you wanted to try to think about a lower bound, get busy. It's open. We don't know. Nobody knows the asymptotics of these numbers. But I, by very little thinking, could show that it was, you know, it grows like a constant to the n squared. So I know something about the log of this number, roughly. And of course, you know, if I ran my simulations and it was outside those intervals, something's wrong with the computer code or something else. So I know a little bit. We also have some data. The data is the data from Knuth's trials, right? I can run this algorithm. It's an unbiased estimate of my parameter, so it's data. let's look at it as data for a second and try to think about it. So remember my statistic, and now I'm going to use the fact that I know how to run this walk and not get stuck, so I never get stuck. So, well, this statistic, T of gamma, it was the product over edges in the path of 1 over the probability of the edge, yeah? And let me just put that up into the exponent the way we do, and let me make it e to the minus the sum over edges in the path of the log, which I'm calling n sub gamma of e, and let me call that e to the minus h of gamma, okay? Where n sub gamma of e is 0 if the probability is 1, log 2 or log 3, and so it's, you know. So this h of gamma is the sum of a lot of little things, right? So maybe it's normal. You know, I mean, that's not such a stretch. You know, that's the sum of a lot. They're kind of random, right? You know, it's sort of going around. Maybe it's normal. And the length of a typical path is around n squared, and so it's not such a crazy thing to say, well, maybe this energy is roughly normal, and it has, you know, mean of order n squared and some standard deviation. And then I could put a prior, as I will in a second, on A and B. And using the data, I can compute a posterior and try to use this as an estimate of the number of paths. Now, that may sound crazy to you, but we'll carry it forward. It's just, what I'm doing is thinking out loud, and you shouldn't do that. It can be embarrassing, but I'm going to continue for a little while. This route that I've just sketched suggests looking at more of the data than just this statistic T of gamma. For example, if I want to say, are these things approximately normal, I could take my 10 billion sample paths, compute h of gamma, and look at them. Look at a histogram of them. You know, just see if they're normal. If I think that the central limit theorem is holding for this, I could look at each path and treat it as a time series and kind of look to see if there's enough enough randomness that the normality makes some sense. So these first thoughts are saying when you run a Monte Carlo trial, there's often an awful lot of information that we don't make use of. We can start to try to think about it, and I'm encouraging us to do that. Now, here's some news. Alas, minus log p of gamma is not roughly normal. This is a histogram from Knuth's data, and you know, whatever this mess is, it's not normal. I mean, you know, we've all looked at a lot of histograms. That's not a histogram. However, looking at the data and thinking about it, and some math that's coming later, it does seem to be that given the length of a path, if I condition on the length of the path, then this statistic minus log p of gamma is roughly normal, and it seems to be quite normal. Well, let me show you what the lengths of the paths are. This is from the data. This is given the length of a path can be anything from 20 to about 100 or so. Here, okay, 120 maybe, and it can really wind around. This is the expected value of, on the left, the expected value of the energy minus log p given the length, and it's monotone, makes some sense. And this is the standard deviation of the energy given the length of the path, and that is like that, okay? And now I could model these as splines and put parameters on the splines and then go to town, and I'm gonna do something like that in a second. But the point again is there is information in the data, and normally we're not led to use it, and this kind of thinking about it in a Bayesian way has led to me to find interesting structure. Let's go forward in this way. Here's a little tiny calculation. Here's what I'm going to do. We started by saying the number of paths is just this sum, the sum of 1 over the number of paths, and that's the sum over the number of paths of P of gamma over P of gamma, and that's the expected value of 1 over P of gamma with respect to this measure on paths. Let's write that using double conditioning. I try to learn how to use this thing. That's the expected value of 1 over P of gamma given the length, and so I've just written that out. That's the expected value, that's the sum over the different possible lengths, 20 to 100, of P of gamma times the expected value of 1 over P of gamma given the length. So here's the trick I'm going to use. These are just, I have a billion data points, and I have, the lengths take values from 0 to 100, so you can do anything you like, but just using the frequencies is all you're going to get, so estimate, the probability that a trial produces a path of length P from the data just directly, or be a Bayesian with that, it won't help or hinder you. And then I'm going to estimate this conditional expected value of 1 over P of gamma from the log normal assumption and using Bayes' theorem, and I'll carry that out and come back and do it. So that's a different way of using the data and my findings to get an estimate of the number of paths. This scheme, remember where I started, which is putting a prior over something strange, and works pretty well, and examples are coming. One point that I want to make now is I did have to think that as I had to snoop around in the data and identify a parameter which in some sense was a sufficient statistic, namely the length of the path. That is, at the moment, I'm running these trials, I've got all kinds of things I could look at. In looking at them, I looked at I found that the length, conditioning on the length of the path seemed to get me out of trouble. And so that was something that took some thinking or some insight, or was something like doing science even, right? Here's a second idea. In this example, and many more that are coming, only a few values of L mattered. These P lambdas, dropped off pretty rapidly, and this expected value was only big for a few values of L. And so instead of having to think, I can try to take this tack, and so this is the theoretical contribution here, which is the following. Try this idea. Let's model this energy minus P of gamma as a mixture of log normal distributions, okay? And you have to pick K, but that's a familiar problem, and I'm going to take K to be 6, and it works great. This picture is a plot of as a function of the length of the estimate of the log of the count. And what you can see is it's very flat there in the middle, and it drops off, and this, well, only a few values of the lengths mattered, and so I don't have to identify the length. Let me just model my minus log P of gamma as a mixture of normals. Now let me say a cautionary thing. The mathematician in me is striking up. It's a fact of nature, a fact of mathematics, that any measure on the line, any probability density on the line, can be very well approximated as a finite mixture of log normals. Okay, so anything can be, so I'm modeling anything. And that's because if you let the mean and let the variance be peaky, you can make a point mass as a normal, and then so the log of P is being modeled as a mixture of normals, but anything can be modeled as a mixture of normals, and so you have to be worried about that. Anyway, let's not, and just go forward. So I now have, say, a mixture of K normals, and I can put a prior on the mixing. Now you have to be careful, and I was. Put a prior on the mixing weights, theta I, put a prior on the means and the variances, call this vector eta, and I should have said this, all of this work is joint work with Mark Coram, a wonderfully innovative fellow at Stanford, and we used k equals 6. I took theta, the initial prior on the on the 6 weights to be uniform on the 6 simplex, and I put independent conjugate priors in the standard way on mu and sigma squared. And as I said before, if I wanted to be more careful, I could model the means and the variances as splines, and I could do that. I haven't carried it out. Okay, the point of this slide is, because there are many other sequential importance sampling problems coming, you don't have to be clever and identify L of gamma. You can try this for any sequential importance sampling. So let me show you what happened. For Knuth's problem, so with all of this story going, I now said, let me start again. I took a fresh sample, not of 10 to the 9th or whatever it was, of 1,000 paths. There they are. I had these paths from my normality assumption. If I accept my normality assumption, I can compute the posterior for this parameter eta, just by straightforward arguments. And now I can sample eta from the posterior distribution, easy to do, and I can compute analytically my expected value of the count or any other statistic, given that it's that mixture of log normals as, sorry, I'm not doing so well at this, but I can try again, as, G of eta is the eta mixture of normals, and then I have to calculate this exponential integral. And this is a histogram of, so sample eta from the posterior, calculate this estimate of the count, do that some number of times. This is a histogram of those estimates of the counts. And from that, you can get a 95% highest posterior interval for the count. And that's, that came out to be, between, 7 times 10 to the 23rd and 1 times 10 to the 27th. And here the quote unquote right answer is, around 1.6 times 10 to the 24th. A point is that this Bayesian procedure that I just went through, and I'm not telling you about a lot of trials that we did to kind of see if it's actually true, seems to be true, got me down from needing, billions of samples of size billions to samples of size 1,000. Well, that's good, right? That's an improvement. Okay, so that's an example, and there are many, many similar problems. Certainly, basic importance sampling, one of the mainstays of scientific computing. You want to calculate an integral. You can sample, perhaps independently, perhaps from a Markov chain, from a different measure nu. You estimate the integral by using the weighted values of the samples. Sequential importance sampling, in case it's new to you, is different in that I'm just building up this measure nu sequentially, and so my weights 1 over p are products, and so this log normal stuff makes some sense. Here's an example, one of many that I've been involved with, counting tables, graphs, etc., with given row sums. This is data that's sometimes called Darwin's data. These are the finches on the Galapagos Island. These are the 18 islands that there were. There's a 0 or a 1 in the ijth place if that finch lives on that island. And ecologists calculate all kinds of statistics to see, is this data different than data which was chosen at random with the rows and column sums fixed? It's a reasonable question how to calibrate their analyses. It's a first question, how many tables are there with the given row and column sums? With Hugo Chen and Susan Holmes and Jun Liu, we built a sequential importance sampling algorithm to do that, and I just want to say a sentence about it because it's just very similar to what I just did. So suppose there are 1, 2, 3, 4, seem to be 4 ones in the first column. So you might think, okay, let me just build up a table sequentially at random, put 4 ones in the first column, and then subtract, 1 from each of those 4 row sums, and then put however many ones have to go in the second column, and just keep going. And that would get you a table, or you'd get stuck. And now there's 2 big steps. The first step is, why not, if the row sums are big, why not make it more likely to put ones in the column, in the rows where the row sums are big? It's easy to do that, as long as you can compute what the probability is that you're putting rows in one at a time. And the second thing is, you can use math. The Gale-Reiser theorem gives you a necessary and sufficient condition on a set of row sums and column sums to be the row and column sums of a binary table. You can use math to say what are the possible next moves you could make and never get stuck. And from that, you can estimate the number of tables, and we're exactly in the same situation. It's a product of a lot of little numbers, and seems as if log normal is a good way to go. This is a huge set of examples, and is the motivation that Knuth had for asking me his question. So in computer science, there's a whole world of what are called backtracking algorithms, and I'll give you a general reference for this, but if you just type it in on the internet, you'll find it. So the issue is, the problem is to find x1 up to xn, some parameters, such that a certain condition, Pn of x1 up to xn holds, where the xi's are, say in integers, sets of integers, they're in some sets Si. In backtracking algorithms, what you're given is some partial constraints. That is, you're given PL of x1 up to xl, so that if x1 up to xn holds, then x1 up to xl holds, the ELF condition holds. And so you can check along the way, and if you can't fulfill if the ELF thing doesn't work, then you don't have to try any of the extensions, okay? So this information is often collected into a backtracking tree. The most famous example is the n queens problems. How many ways can you put n queens down on an n by n board in such a way that they're non-attacking? There, XL is the column of the queen. The queens have to go all in different rows, and x1 is what column is queen 1 in, and x2 is what column in queen 2 is, and they're between 1 and n. The condition, Pn of x1 up to xn, is, well, they shouldn't be, they shouldn't be in the same column, and they shouldn't be on the same diagonal. And those same conditions hold for everything. This is the backtracking tree, so you could put the first queen in any of 4 places, 1, 2, 3, or 4 columns. This is in a 4 by 4 case, I should have said. And then you can continue, and you get stuck here, and then you backtrack. I won't try to explain backtracking too carefully. There are 2 solutions here, 2 ways of putting 4 queens into a 4 by 4 board. Here's the for real chess board, the 8 by 8. There are 92 solutions, and backtracking, you start to go, and then you stop, and you don't have to check anymore on that branch. Allows. Oh, I didn't want to do that. Well, I can just go forward. Backtracking allows you to scan this whole backtracking tree using 1% of the 8 to the 8 cases. What Knuth was interested in doing, so backtracking algorithms, when you run them, some of them run lightning fast, and some of them just take weeks, and you don't know if it's going to be months or years, and how to estimate the running time of a backtracking algorithm was Knuth's issue. And he had the following scheme, which is just sequential importance sampling, but let's say what it is. So you start to build a path at random, but don't backtrack. Just start to go down the tree, and each time making one of the available choices uniformly. If you are at level I, if you have DI places to go, that's DI for that path. And then exactly the calculation that I did, it essentially shows that, that this statistic, T, you never get stuck, you just stop when you get to a leaf, which is D1 plus D1 times D2 plus et cetera. This has, under this random sampling distribution, exactly the number of vertices. And if you wanted to know something else, you could use these as important sampling weights. Here's an example in the 8 queens problem. The first queen, went there. The second queen went here, and the queens, they got some place along, and then it was stuck. There was no place to go. And when you multiply the number of choices as you went down the tree, the estimated number of vertices, the total number of vertices in this graph was 2129. A second trial was 2689. A third trial was 1489. So these are partial estimates along the way. And even from doing it a few times, these 4 numbers give you some reasonable idea of how many vertices are in this tree. Here, it turns out the right answer is 20,057. And in this example, you can blast it out. The minimum statistic, it says down here, is 489. The average, this is an unbiased estimate, is 22,057. The max is 7,500, and the standard deviation is of the same order as the mean. And so you could estimate accurately how many vertices there are in this tree using backtracking. And okay, let me go on. The points are, any sequential importance sampling scheme, and there are thousands of them, fits into this tree, this backtracking tree picture. Knuth's self-avoiding paths problem, you're starting to build a path, you just, make a tree out of the possible choices that you have. So they all fit into that. Pick a path in a tree at random and add the log degrees along the way. Will give a mixture of normals with length as the mixing variable. So that's a theorem. Okay, now I have to make some assumptions about what kind of paths and trees, but under reasonable mild conditions, in particular for the 8 queens problem or n queens problem, for Galton-Watson trees, this heuristic that I came upon with Mark is in fact a theorem. That is that things are mixtures of log normals. If you wanted to read more about backtracking, and in particular see this method of sequential importance sampling used in very interesting real problems, Knuth, so he asked me this question when I started at Stanford in 1974, and he just now is coming to write volume 4B. and if you look on his website, Introduction to Backtracking, The Art of Computer Programming, volume 4, prefascicle 5B, it's a 100-page book on backtracking and sequential importance sampling. And I did quite a lot of math about sequential importance sampling that I'm not telling you about, but in a paper with Saurav Chatterjee, the sample size required in importance sampling, and it's on the archive or on my webpage, which analyzes Knuth's algorithm in more detail. It might well be that this is my last slide. So back to the big picture. There's a question, and I don't know the answer to it, but collectively we know more than I do. So what kinds of information are available in our Monte Carlo simulations? We often use pitifully little because that's all we have time for, that's all we think we care about. When I look at what I do or what my compatriots do when they analyze their Monte Carlo, there's whatever statistics they're interested in, and then they might put some test statistics in, because the standard way of calibrating is to take a bunch of test statistics and see if they seem to settle down. So we often have a handful of functions that we monitor along the path, and so that's some use that we make of the information. That people do things like computing effective sample size. Occasionally you'll see somebody reusing their samples by bootstrapping, and that's about all, I mean, that I see. Now, there should be a big literature on this, and I only know of one paper, and I'm sure I'll learn many more, so thank you in advance. I know of one paper which has a very similar theme, but then went in quite different directions. Augie Kang, Peter McCullough, Xiaoli Meng, and Dan Nicolai, and I don't know Mr. Tan's first name, wrote a paper called A Theory of Statistical Models for Monte Carlo Integration, and it wasn't Bayesian, but I'm sure that's because Peter McCullough would never have his name associated with anything Bayesian. But the ideas are somewhat similar, that is, trying to model things, but then the problem that they focused on was different. This article is a discussion article in the RSS, and there were many interesting comments, and many of those commentators, some of whom are here in the audience, wrote papers as follow-up papers. So if you type this paper in, and then you look on Google Scholar who cited it, you'll find the literature. So it's not very much, but that's a way of finding it. I'm not the only crazy one, if you want to put it that way. This story I've just told you is a special case of what I call Bayesian numerical analysis. That is, you have an integral or a sum you want to do. Even if you have a complicated formula for it, you don't know what it is. So put a prior on, get some data, compute posteriors, and use Bayes methods to get improved estimates. I wrote a paper about that a long time ago, in which I traced the history of it back to Poincaré. Nowadays, it's slightly fashionable under the name of uncertainty quantification, and Jim Berger gave a talk, and he said, well, the engineers did it in 1960. Well, Poincaré did it in 1890. So, okay. And many, many other people well before the engineering literature. Stefan Lauritsen did wonderful work on it in estimating what the force of gravity is in the 1960s, I'm going to say. So this paper also, if you look who cites it, it was completely unsighted, and then all of a sudden it's blossomed. And in fact, there's a marvelous website which is called probabilisticnumerics.org, and you can find what literature I know about. So the theme of this talk was, it would have been natural to call it, Bayesian thinking about Monte Carlo, but I don't think, I think that just thinking is a Bayesian activity. And I think Finetti encouraged us to use what information we have and try to combine that with what data we have in innovative ways. This is another little petal in the flower. The reason I decided to give this talk is I think many, many people in this audience have noticed, why don't I ever use Bayesian methods when I analyze my Monte Carlo data? I'll be happy to hear, examples, references, thoughts. The collective power of this group is much more than any one of us, and thank you very much. Thank you.
All right, well, first, I'm very honored to start a discussion for this first Finetti lecture. The second thing is, this is the first time when I write my discussion about 6 months before the talk, because actually, as it happens, there was this NIPS workshop last December in Montreal, which was about probabilistic numerics, and whose starting point was Persi's 1988 paper. And so I was invited not as a specialist, but as a skeptic, and So my talk was actually a discussion of the pros and cons of probabilistic numerics. And so I decided to adapt those slides because it somehow fits very well Persi's talk. Okay, and so I'll go through four names: Larry, Charlie, and Persi, which all ends by E. The first one is Larry's constant, and this is a problem that has bothered me for quite a while. So I mean, if you have not read Larry's book, and this question is exactly this problem of having a constant, not the 37th digit of pi, but a constant that is entirely defined from the fact that we are dealing with a density, but we don't know it. And so could we analyze this problem from a Bayesian perspective? And so that's how Larry puts it as an example in his book, where, I mean, you can come up with a frequentist solution for approximating C from, say, non-parametric estimator of F. So F hat over G is an estimator of C, and if you take more data or more simulations, you end up with a proper approximation to C. And so if you turn to a Bayesian resolution, a sort of naive Bayesian approach is to say, well, I'll put a prior on C because I'm Bayesian. And so if you start with this naive prior on C, you end up nowhere because your data, say your simulation, doesn't transfer into information about C per se. I mean, it's a simulation from F, and so you have to go around the corner to come up with an estimation of C. But if you write it as a naive Bayesian, which Larry pretends to be in this text, you end up nowhere, okay? And so those are comments I made 6 months ago that maybe I've evolved a little bit about it, but the first interpretation is that, well, it's not a statistical problem because there is no likelihood per se if you write it that way, okay? And so there is no data from your simulation about C. So if you take it at face value, you are not analyzing something that is statistical. And so you have to go somewhere farther to come up with a statistical solution, which is a way of probabilistic numerics. Namely that you have to model F or G through a prior, rather than just the mere C that by itself is isolated and cannot be informed through simulations. Okay. And somehow it relates to a larger part of problem, and that connects with Persi's talk that, I don't know if you noticed, but the Knus solution for the number of paths is one harmonic mean estimator in the sense that it is an average of 1 over a probability or a likelihood. And in that case, I mean, this is a finite universe, so there is no problem of infinite variance, but still, using an harmonic mean estimator means that you are subjected to these huge jumps by a few small values of P of gamma that takes 1 over P of gamma to be very large. Okay. So, I mean, that's maybe one reason why it's hard to come up with a solution, that harmonic means are not the best Monte Carlo estimate if you look at that at face value without the shrinking or regularization approach of probabilistic numerics. Okay. And that relates to other problems I don't want to mention too much here, but somewhat, and that's another worry that connects to Persi's talk, that when we approach Monte Carlo, the first thing we want to see is unbiasedness, and that kind of creates a huge tree that hides a forest of problems that by trying to stick to unbiasedness, as we shouldn't as Bayesians, we just cut ourselves from more efficient solutions. So, I mean, massive prediction of simulations to reach a proper estimator sticking to unbiasedness is not necessarily an efficient thing. And then that connects to something that has been part of the folklore because never really published, which is Charlie's regression. And so this is Charlie Geiger, we came up with an approach to constant estimation, so it's a typical Monte Carlo integration problem, as a true statistical problem through regression. So if you have a collection of unknown normalizing constant associated with densities, and if you produce simulations from all of those densities, if you merge them together, you can create a likelihood that involves this unknown normalizing constant. That is a logistic regression. That is, you merge all your samples and you try to reallocate each simulation to one of the densities. So this is hiding some of the information you had at the beginning, but through this modeling, you do end up with estimates of your constants, which is a bit of a miracle. But it has a very interesting appeal that it brings a constant into the statistical model. Okay. And so, I mean, this is a non-Bayesian solution, but if you can derive Bayesian versions of that by putting an extra prior. Okay. And you can start bringing up a statistical, more global statistical approach through this modeling. And surprisingly, the paper by Geyer was never published, but it's still available, and it's still known in the community. I won't mention much Kong et al. Now because I'm connecting with that later. But there is actually a larger collection of approaches through partition modeling and partition functions that does the same thing, that kind of hides part of the information in the original model and then re-estimate it as a statistical approach. Okay, I'll skip that. And then we arrive to Shirley's Emily. So this is a set of slides that Shirley made for an RSM workshop I attended, where I started to understand much better the 2003 paper. And of course, I mean, you cannot look at the details, but this was a re-explanation of the JRSSB discussion paper, where Kong et al. Explain how to set, again, a constant estimation problem as a statistical model, and ending up as an MLE where it was a semi-parametric MLE. So, I mean, I will not read the detail, but there is this connection with Charlie's solution. And yeah, the end point is that you can estimate a density or a constant as setting a maximum likelihood estimator on a purely numerical problem. And those pictures were made by my daughter when I discussed the paper at the Royal Society. And again, there is something very surprising that you start as a numerical problem, and then you set it in a different way, so that you end up with statistical solution to the point of producing Fisher information for the precision, and some solutions of partitioning that are a form of Rao-Blackwellization. Okay. And then we come to the last point, which is Persi's numerics. And this is a paper of 1988 that I remember discussing with George Casella at about that time. Well, actually, we were waiting for his car to be repaired, and we were sitting in a cafe, and we started discussing that as something very exciting. At the end of the cafe, we couldn't have better ideas, but we thought the idea very, very exciting. And then a few years went through, and this was not followed by something very, very conclusive until this probability numerics community came more from engineering background and machine learning. And in particular, my colleague at Warwick, Mark Girolami, started promoting the use of Bayesian and probabilistic modeling of functions as a way to improve considerably the resolution of integrals or partial differential equations or optimization problems. And so, I mean, I won't go into describing what it is, but usually there is a Gaussian process somewhere in the picture, so you can see the connection with machine learning, where that Gaussian process has to be used at some point. And then this is your prior on an object of any complexity and any structure, so a function that you want to integrate. And this Gaussian process prior is merged with simulations or data to return a posterior, a real posterior in the sense we understand posteriors, in a functional space that gives you both estimators for the functions, the integral, the differential equation, and imprecision evaluation as we should have. Okay, so there is a variability assessment. Okay, and of course this is somewhat arbitrary. Why a Gaussian process? I mean, it is very concentrated in the space of all functions, but this is not something you have to believe as something from nature. It's just a tool to model a huge unknown into producing a better estimate. Okay, so I don't want to take all the time, but let me move to my last slide. Maybe I had another one, sorry, here. That, I mean, we can discuss some aspects of this as being arguable, but for instance, what sense do you put on the probabilistic modeling on functions, and this notion that functional species are very large, but there are ways that you can return something rather than nothing in a reasonable time, like when you move from 1 billion simulations to 1,000 simulations. So if you can produce some more results around coherence, because again, we are in spaces where we're not sure Bayesian inference is always coherent, that's a big plus that we should pursue. And the community is growing as demonstrated by this NIPS workshop last year. Now, let me put a few personal words about evolution and the shift about Monte Carlo ascertainment and how we could conduct Monte Carlo analysis. There is one thing that we always forget that when we try to approximate an integral, which is that no matter how complex the space X is, where we conduct the integral, at the end, the integral is a real number. So we move from a very large space or a very complex space onto the real line. And often we just don't see that part. We rush into simulation, say, from a certain density F, and only later project onto the real line. And I say it would be an improvement if we could conduct the alternative analysis that, by getting around the curse of dimensionality, try to project first and then run the simulation. And there is one illustration it is not completely clear to me, but with nested sampling is this technique introduced by John Skilling to approximate the marginal likelihood in Bayesian inference. And one very nice part of nested sampling is the concept that it is a one-dimensional integral. And so John Skilling starts by reducing the problem to a 1D problem of the distribution of this likelihood under the prior. And the likelihood is a 1D object. After the simulation gets a bit hairy and imprecise and not necessarily very efficient, but the simulation is under the constraint that the likelihood is at the high values, which is a projection in dimension 1. And so in that direction, I think there are many ways to explore and to construct estimators that will benefit considerably to the Monte Carlo issue. And so let me conclude by thanking Persi for his talk and for his numerous contributions to our field that we will explore for years and years to come.
Standard deviations are very common thing that we use in summarizing Markov chain Monte Carlo results and things of that sort, any kind of Monte Carlo results that are used to support Bayesian analysis. That's my primary interest. In many cases, we have better options available, but it's remarkable how often they're not used. And a particular case in point is the idea of conditioning, or what we've come to call Rao-Blackwellization, which is pretty much always possible if you're using something based on full conditionals. It's, you know, if you just look at papers in which people show plots of marginal densities that are a little bit bumpy, you know they plotted a kernel density estimate rather than something based on taking advantage of the available conditional distribution. There's some good reasons, a number of good, maybe some not so good reasons why people do this. Keeping it simple is useful, and in particular, sorry. Let's see if I get this right. In terms of thinking about sort of priorities when we're writing a paper, if it's in a particular scientific context, that's by far the most important thing that we want to spend our limited number of pages talking about. Then the models and prior distributions that we're going to use need some time. What's an appropriate summary of the posterior distribution? You know, if it's a symmetric distribution, a mean is fine, but if it's heavily skewed, we want to focus on a median. Then focusing on maybe the supporting methodology for doing the computation, simulation, typically for us. And only at the last stage do we want to have to discuss and defend the output summary method. And at that point, well, if X bar is good enough, let's just stick with that, is I think often a thing we do. Another factor is the software we work with. If you're using something like Bugs or JAGS for your simulation, that's going to know about conditional distributions and things of that sort. But if you then pass on the results to something like CODA and BOA, that information is not transmitted about what the full conditionals are. You can write them down yourself, of course, and implement them, but it's not only is it more work, it's also another thing you could get wrong. Again, if it's good enough, that's a good, big reason why we do tend to stick with these simpler things. In a kind of context where it is common to use Bayesian methods are situations where we have maybe very strong information for some simulation settings, but nothing in between. Classic examples are computer experiments where you for certain parameter settings, you run expensive simulations, get data. In between, you have nothing, but you may be willing to assume smoothness, so you use some sort of Gaussian surface priors to allow you to then compute some some intermediate results together with uncertainties. The sort of numerical integration ideas that Persi mentioned and that Chris talked a little about, the numerical Bayesian analysis ideas are similar in that you have good information at points and you fill things in between. Looking a little bit at the self-avoiding random walk, to help me understand what's going on here, I wrote a little my own version of this, and I'm not sure I got it quite right in the sense that I have a different length distribution from the one that Persi described. It's a bit lower. I am confident that my method is producing a process that could potentially hit all of the self-avoiding paths between the two corners, and any such process is going to give you the right estimate. I might not be using exactly the right one. I didn't have a chance to go back and look at the details of Knut's approach, but I think qualitatively still what I found will apply. At least with my simulation, I get a distribution of those negative log probabilities that is not normal, but could well be approximated as a mixture of normals. On the other hand, we do have this problem that the estimate is involved a sum of the exponentials of these guys, and so the small values just don't contribute very much. In fact, what I have here is is the red curve is a CDF of this. The black curve shows the percentage contribution to the sum that comes from the different values cumulatively. So basically nothing is accumulated until you get down to there. And another way of saying it is that the 99.5% of the final estimate comes from the upper 0.5% of the distribution. So in terms of modeling, for my approach at least, if I use a model for this, it's not going to do very much for me because that's really what I have to get right, way extreme upper tail. And that's very difficult to model properly, at least for me. And I have to think about what can I do to convince myself that I've got a good model, and then can I convince a referee that this is going to be a good thing to do. So definitely modeling is very good if we can get things into the middle of the distribution where we can use our models effectively. The tails, it could be a little trickier. It is easy in this case just to throw CPU cycles at things, so I ran 100 million observations in parallel. Took only a little over an hour. When I batched those up into 100 batches of 1 million each and computed estimates from each, I get this distribution of the estimates, take the logs of those estimates, and I get something that's still skewed, but at least now we're in a situation where our final estimate, which is going to be around there, our mean, our overall mean, is in the middle of the distribution. And I would feel comfortable trying to model this situation to try and extract more information from it. And so the one point I think I drew from my experiments is applying modeling once you've done some batching may be a useful thing to do in some situations. So just to finish up, it's very useful to think about trying to take advantage of theory that we have, or just things that we can observe by looking at some of the structure of our data and using modeling to help allow us to perhaps get away with smaller sample sizes. And there's some really nice ideas about that in Persi's work. I'm a little less confident if things really are dependent on tails and need to require tail modeling, which is just something I at least don't know how to do terribly well. Batching may be something that helps, and of course one thing to think about is can you change the simulation so it spends more time in the tail, the classic idea underlying importance sampling. Thanks for a great talk.